Welcome back, everyone. Now that we've had an introduction to the concept of what a mole is and the concept of molar mass, we're going to apply those concepts in various situations that will give us an introduction to other types of quantitative work we will see in future chapters. Let's start here in Part C of our Chapter 5 lecture note outline, where we're going to start talking about something called a hydrated salt. And we're going to use molar mass with hydrated salts to do some interesting things. Hydrated salts are ionic compounds that have water molecules trapped inside the crystal structure. Because water is trapped inside of the structural formula, it makes the molar masses of these hydrated salts heavier, and it also changes some of their properties. As an example, take a look at the hydrated salt of copper sulfate. This particular hydrated salt has 5 water molecules trapped inside of the crystal structure along with copper and sulfate. We get this beautiful blue crystal structure because of the way the water molecules are arranged around the copper nucleus. When hydrated salts are heated, water is released from the hydrated salt, leaving behind just the part without the water. We call this the anhydrous salt, or the part without water. One of the really neat things about copper sulfate is if we take the anhydrous form of the salt, that is, the form that doesn't have the water around the copper metal, which looks kind of white, and we drip some water into it, it will start to turn that beautiful bright blue color again as the water starts to surround those copper metal ions. Hydrated salts are named like regular salts, with an additional component that specifies the number of water molecules trapped inside the structure. For example, the salt that we were just discussing is called copper sulfate pentahydrate. In this name, we see that there is copper, sulfate, and water by the word hydrate. Now, we're curious how many of those water molecules there are, and we can determine that by looking at the Latin prefix in front of the word hydrate. In this case, we see penta is being used, and we know that penta means 5. So there are 5 water molecules in the formula for copper sulfate pentahydrate. Let's write down the formula. First, we'll start by writing the formula for copper sulfate. Now, copper is a transition metal with a variable charge, and its most common forms are the +1 and +2 forms, with the +2 form being significantly more stable. Let's suppose then that we're talking about copper 2 sulfate pentahydrate. Since we're talking about the copper with a +2 charge, that means the formula copper with 1 sulfate ion is correct for this first part of the formula. Now we have to show the part of the formula that has the water molecules taken into account. To show a hydrated salt, we separate the main salt from the hydrated portion with a dot. This is called the hydrated salt dot notation. So we put this dot here, and then next to it, we're going to show how many water molecules are present in the formula for this particular example. So we put a 5 and then H2O next to it to indicate there are 5 water molecules for each of the copper sulfate salts. So that's how we handle hydrated salts. We describe them as a prefixed hydrate, where the prefix is a Latin term that refers to how many water molecules there are in the formula. When we're writing the formulas out, we use the dot notation with a coefficient in front to represent that Latin prefix, and then the formula for water right next to it. Let's try another example, and this time we're going to actually write down the name for the formula that we're given of a hydrated salt. So the first thing that we're going to do is try to determine how many water molecules there are in the formula for this particular hydrated salt. We see the coefficient 2 in front of water, so that tells us there are 2 water molecules. To write down the name for this example, we're going to start by writing the name of the salt, followed by the word hydrate. We're going to use a Latin prefix in front of the word hydrate to indicate how many water molecules are in the formula. Go ahead and pause the video and see if you can write the complete name down. So our name should start with the name of the salt, which is barium chloride, followed by the hydrate portion. Because we have 2 water molecules here, we use the Latin prefix di, and that's right in front of hydrate, and so our full name is barium chloride dihydrate. Now, because hydrated salts have additional water molecules in their formula, that means their formula mass or molar mass is greater than the anhydrous salt because the presence of water adds additional mass. Because we're going to be doing calculations with hydrated salts and their masses, we need to know how to figure out the formula mass for a hydrated salt. The formula mass for a hydrated salt is simply the molar mass of the salt itself plus the total molar mass of all of the water molecules in the formula. So if we wrote out a formula for this operation, it would look something like this. To the molar mass of the salt, we would add the molar mass of water times the Latin prefix number for the number of water molecules. So for instance, we have a dihydrate here. That Latin prefix means 2, and we would therefore multiply the molar mass of water by 2. So X here represents the number of H2O in the formula for the hydrated salt. Here's a quick tip for you. Because we use the molar mass of water so frequently in calculations, it's really handy just to be able to know what it is without having to recalculate it each time. So you might want to remember that it's 18.02 grams per mole. And of course, we get that when we add 2 hydrogen atomic masses to 1 oxygen atomic mass. So oxygen is 16, and each hydrogen is 1.008. So that gives us a total of 18.02 grams per mole for water. So let's calculate the formula mass for barium chloride dihydrate. First, we need to have the atomic masses of barium and chlorine. Barium's is 137.3 grams per mole, and chlorine is 35.45 grams per mole. Because we have 2 chlorine atoms in the formula of barium chloride, we need to multiply that molar mass of chlorine by 2 in order to take both of those atoms into account. So just for the salt portion of this molecule, we have barium, which is 137.3, and the total amount of chlorine, which adds up to 70.90 grams per mole. Now we just have to add all of this together, the barium, the chlorine, and the water component, to get the total formula mass. So if I want to show all of the work here, I've got 3 terms. It's 137.3 for barium, and that's grams per mole. Then we're adding that to the chlorine mass, which is 70.90, and then we're adding in water, which is 18.20, but of course I'm multiplying that by 2 because we have the dihydrate here. There are 2 water molecules. Let's add all of these up and then make sure we round it to the correct precision. So after all is said and done, we have 244.2, and that will be grams per mole, but let's just double check here that the precision is correct. Look at each of the terms because we're adding them together, and look at the last significant digit and find the one with the least precise value. We notice here the first term, which is for barium, only goes out to the 10ths position, whereas the others go out to the 100th position. So that means that mass, the 137.3, is the least precise, and therefore our final answer needs to be rounded to that precision as well. And finally, let's not forget to put all of the units in. For each case, we're adding grams per mole, so therefore our answer will also be in grams per mole. Now let's take a look at this question example that I have here below. It says if we had 0.275 moles of barium chloride dihydrate, how many grams would that weigh? So this is an example of how we can use the molar mass of this hydrated salt to do a calculation with it. Remember that we can use molar mass as a conversion factor between moles and grams or grams and moles. So let's try to set this one up. We're going to start here with our moles of barium chloride dihydrate, which is 0.275, and then we're going to multiply it by the conversion factor that will transform moles into grams. So this conversion factor needs to have grams in the top position and moles in the bottom position. So if you look at the units in this conversion factor, it's grams over moles, or grams per mole. And as you learned in the previous lesson, when we have grams per mole, that's the same as molar mass. So as far as values go, we would have to put in here the mass that exactly 1 mole of barium chloride dihydrate would have And remember, we calculated this in the previous step. Now we can arrive at a solution simply by multiplying our moles of barium chloride dihydrate by its molar mass in grams, and this gives us 67.2. Notice our answer here needs to be rounded to 3 significant figures because the initial term that we started with also only has 3 significant figures. Now, what about units? Notice that moles of barium chloride dihydrate is down here, and moles of barium chloride dihydrate is also up here, so these units cross-cancel. That leaves us with the last unit remaining, grams of barium chloride dihydrate. So that's an introduction to what a hydrated salt is and how we can go about calculating the molar masses for hydrated salts. Let's go to the next page and look at a few more applications of moles and molar mass. Now on the next page, which follows in the lecture notes, I have an example of a problem that might be a little bit advanced for this stage at the moment. So for now, let's go to the next page and we'll come back to this a little later. Here in part 3, we're going to learn another aspect of quantities in chemistry. Specifically, we're going to be learning about mole ratios. What I mean by that is we're going to learn how to build conversion factors from chemical reaction equations. Before we learn how this works with reaction equations, let's start somewhere a little simpler. Let's start by looking at the conversion factors that we can build from a simple chemical formula. Let's start here with this first example, which asks, how many moles of nitrogen are in 1 mole of lead nitrate? So what we're going to do here is we're going to make a conversion factor where we show lead nitrate in one position, maybe on the top or maybe on the bottom, and then nitrogen in the other position. This is a conversion factor that we can build from the chemical formula for lead nitrate. To do this, the first thing we need to do is find nitrogen and figure out how many nitrogen atoms there are in a single formula unit for lead nitrate. So notice nitrogen is right here. While a single nitrate ion only has 1 nitrogen atom in the formula, each lead nitrate has 2 nitrates in the formula. So that means each lead nitrate actually has 2 nitrogen atoms in it. So if we built a conversion factor out of this information, it would look something like this. We're expressing the ratio of moles of nitrogen to moles of lead nitrate. And if we have exactly 1 mole of lead nitrate, that would mean that we have 2 moles of nitrogen. So let's put the 2 value in that blank space. So now we have a conversion factor that would let me transform moles of lead nitrate into moles of nitrogen or moles of nitrogen into moles of lead nitrate. We got all of this information, this quantitative information, from the formula for lead nitrate. Let's try another one, but this time I want to give you a chance to try it yourself. Here we have the question, how many moles of oxygen are in 1 mole of lead nitrate? So what I want you to do is build a conversion factor that expresses this relationship. So go ahead and pause the video, and when you unpause, we'll discuss. So you should start off by having a ratio of moles of oxygen to moles of lead nitrate. Now, if you had lead nitrate in the top position and oxygen in the bottom position, that's fine as well. We're just trying to show the ratio of the two, and it doesn't matter which one is on the top or the bottom. So anyway, we have this for every 1 mole of lead nitrate, how many moles of oxygen are there? So if you look at nitrate, there are 3 oxygen atoms in each nitrate. So we at least have those 3, but notice that we have parentheses around it, and there's a 2 subscript here. That means there are 2 nitrates for every lead nitrate. So we have a total of 3 times 2 oxygen atoms, or 6. So let's put a 6 here. So now we have 2 different conversion factors. We have a conversion factor that would let us convert between moles of nitrogen and moles of lead nitrate. And we have another conversion factor that will let us go between moles of oxygen and moles of lead nitrate. Now let's take a look at this next example here, which lets us use these conversion factors. Here we see how many moles of nitrogen are in, say, 0.543 moles of lead nitrate. So how do we go about doing this? Well, what we're being asked here is to convert moles of one thing, one type of substance, into moles of another type of substance. So in essence, we want to go from moles of A to moles of B, where moles of A is our starting point and moles of B is our destination. To do this conversion, we need a conversion factor, and the conversion factor necessarily needs to have units of moles of A on the bottom and moles of B at the top. The specific values that we use in this conversion factor, which I've shown here as X and Y, have to come from the mole ratios that we derive from the formula. So let's try this out with this example. First, we need to identify our starting point, our moles of A. Because we're told how many moles of lead nitrate there are, that's our starting point. So we have 0.543 moles of lead nitrate. Now what we need to do is multiply this starting point by our conversion factor. And again, the conversion factor needs to have moles of lead nitrate on the bottom because that's our starting point. And we're converting that moles of lead nitrate into moles of nitrogen. So necessarily, the units moles of nitrogen will be in the top position. Now we just need to find the values that go in front of each of these units. Where do we get those from? That's right, we get them from the formula. Say, for example, that had exactly 1 mole of lead nitrate. How many moles of nitrogen would there be? That's right, there are 2 moles of nitrogen for every 1 mole of lead nitrate. So now we just have to multiply 0.543 moles of lead nitrate by 2 and then divide by 1 and we get 1.09 moles of nitrogen. Let's take a look at this next example. How many moles of oxygen are in 0.215 moles of lead nitrate? Go ahead and pause the video and see if you can set up the starting point, the conversion factor, and then get the value for this example. Our starting point here is the 0.215 moles of lead nitrate. Then we multiply that by a conversion factor, which will convert moles of lead nitrate into moles of oxygen. Now, if we had exactly 1 mole of lead nitrate, how many moles of oxygen are there? That's correct, there are 6. So we have a 6-to-1 ratio here. We can get the final value, which is 1.29 moles of oxygen, simply by multiplying our 0.215 moles of lead nitrate by 6, and then, of course, dividing by 1 to give us our final value here. Now, there's a third example down here, which I've actually been meaning to delete from the lecture note outline, as it is slightly redundant. Now that we've learned how mole ratios work, let's go to the next page and learn a few more applications. It can be very useful to have the identity of a chemical compound and need to be able to determine the specific amount of mass that one would be able to isolate if they purified that compound and extracted all of one type of element. You can imagine this type of work might be useful in, say, the mining industry or in other chemical industries where we take some raw material and we want to extract out something more valuable from it. I refer to this as calculating mass composition because we're trying to find the mass that one component of this compound has in a given sample. We can use mole ratios from a formula to help us do it. Now I've outlined the steps up here in this box, which is basically we're given the mass of a compound and we're being asked what is the mass of an element within that compound. Let me show you how we can do this, and we're going to start with this example, which is how much pure copper metal in grams could be recovered if we had 15 grams of blue copper sulfate pentahydrate crystals. So you can imagine that we have some of those blue crystals I showed you earlier, and we wanted to refine these to get out just the pure copper. How much copper could we get if, say, we had 15 grams of this blue stuff? Now, the first thing that we need to do is we need to have some conversion factors that let us go between moles and grams and moles. So in order to do that, we're going to first need to just start with the formula of the starting material. So as we learned earlier, we can write down the formula for a hydrated salt by using the dot notation. So here we have the formula for copper 2 sulfate pentahydrate. Now what we need to do in step 2 is we need to calculate the formula mass for this compound. So let's go ahead and add up all of the atoms in this, including the copper, the sulfate, and the 5 water molecules. Going over to the periodic table, we find copper has an atomic weight of 63.55, sulfur is 32.07, and each oxygen is 16. We have 4 oxygen atoms, so we need to multiply that 16 by 4. And we have water, which is 18.02 grams per mole for each one, and there are 5. So we need to multiply 18.02 by 5. Once we add all of this up, we get 249.72, and that's units of grams per mole. So copper 2 sulfate pentahydrate has this formula mass. Having that value is going to allow the critical step of converting the 15 grams of copper sulfate into the number of moles of copper sulfate. So let's go take a look at the next step and see how all of this works. Now, what I'm about to show you is one of the key problem-solving skills that you're going to use throughout the rest of the course whenever we're doing this kind of quantitative work in chemistry. The basic idea here is that we have the mass of one thing that we want to convert into the mass of another thing. So I've represented that here using the words mass of A and mass of B. So we want to be able to convert the mass of A into the mass of B. Now, there's a problem with this. It turns out there's no direct route for converting the mass of A into the mass of B. Now, even though there's no direct route, it turns out there is a series of steps we can do that will allow us to accomplish this. And we're going to see this same series of steps many, many times throughout the rest of this course. So I wanted to start teaching this method to you now. Now, as you've seen, it is possible for us to convert the moles of A into the moles of B. We just saw that earlier where we converted, say, the moles of lead nitrate into the moles of nitrogen. We can do that generally with any of the formulas that we have or reaction equations later on. We can definitely convert moles of one thing into moles of a totally different thing. The way we do that is we find the mole ratio between A and B. I like to call this conversion where we go from the moles of one thing into the moles of something totally different, the mole bridge, and we're crossing the mole bridge when we do this type of conversion. Now notice that this is just converting moles of A into moles of B. I haven't done anything with the mass of A or the mass of B yet, so I need somehow to go from mass of A into the mass of B. How can I do that? That's right, I can use the molar masses to allow me to convert between mass and moles. So we've already learned that molar masses are the conversion factor to go from, say, grams of A into moles of A, or from moles of A back into the mass of A. We can use molar mass as that conversion. So if we wanted to go from the mass of A to the mass of B, we would need to do 3 steps. First, we're going to convert our mass of A into moles of A by using the molar mass of A. Then, I have to cross the mole bridge. I have to go from moles of A to moles of B. Once I have moles of B, it's a simple matter for me to go back into the mass of B simply by using B's molar mass as a conversion factor. So a total of 3 steps. These 3 steps we will use over and over to go in different places around this map. And the key part of this map is the mole bridge. The mole bridge is this special thing that lets us convert between one type of compound or element and another type of compound or element. So this mole bridge we'll see is very important, and I want to show you how you can always build a nice solid conversion factor for this mole bridge. So that's an overview of the method that we're going to use. Let's actually try it with this example. We're starting again with 15 grams of our compound A, which in this case is copper sulfate pentahydrate. So let's write down the starting point and maybe our first conversion factor. So here we have our starting point, 15 grams of copper sulfate pentahydrate. That's our mass of A. Now what we're going to do is convert this mass of A, the 15 grams of copper sulfate pentahydrate, into the moles of copper sulfate pentahydrate. So I need a conversion factor that has grams on the bottom and moles on the top. Let's see what that looks like. So our first conversion factor here has the units of grams of copper sulfate pentahydrate at the bottom so that it can cross-cancel with our grams of copper sulfate pentahydrate over here. That's our starting point. Our destination in this first step is moles of A, and A here is copper sulfate pentahydrate. So in the top position, we have moles of copper sulfate pentahydrate. This ratio, you'll notice, is moles to grams, which is molar mass. So here in this first step, we're converting between the mass of A to the moles of A using the molar mass of A. So we need to have these values. We need specifically the amount of grams that exactly 1 mole of copper sulfate would weigh. We calculated this value in the first step of this problem, and we found that 249.72 grams is exactly 1 mole. So let's check off our first step here. We've converted between mass of A and moles of A, so we can just check that off. Now notice I'm not going to write an equal sign here. I'm going to continue doing my conversions because it's a lot easier to set it up that way. So now we're going to have another conversion factor. And we're going from now moles of A to moles of B. So this is where I'm going to build my mole bridge. What does this mole bridge have to look like? Well, that's right. It has to have the two different compounds that I'm converting between. So for example, we're going from copper sulfate pentahydrate into copper. These are two totally different compounds. So my destination here is moles of copper, so that should be in the top position. And where I'm coming from is moles of copper sulfate pentahydrate. That's down here. So we have two different compounds in this ratio, and this is why it's called a mole bridge. We're going between moles of one thing to moles of another thing. So where do we get these values from? Well, if you need a hint, think about it this way. What if I had exactly 1 mole of copper sulfate pentahydrate? If I had exactly 1 mole of copper sulfate pentahydrate, how many moles of copper would I have? That's right, because each mole of copper sulfate pentahydrate has 1 copper atom in the formula. That means it's a 1-to-1 ratio. So 1 mole of copper sulfate pentahydrate is equal to 1 mole of copper. And there's our mole bridge. So having that conversion factor means we've completed the second step. So let's cross off our mole bridge step up here in this diagram. So now we've completed 2 steps in our conversion overall. We've gone first from the mass of A to the moles of A. We then converted the moles of A into the moles of B. Now we need to convert moles of B into the mass of B. So how do we do that? Well, that's right, we need the molar mass of B. B in this case is copper. So we're going to have another conversion factor over here with units that convert from moles into grams of copper. Let's see if we can set that one up. So take a look carefully at what units we need here in this last conversion factor. We're coming from moles of copper, so we should definitely have moles of copper in the bottom position. But what goes in the top position? That's right, we're trying to get grams of copper, so grams of copper needs to be in the top position. So we should have a conversion factor that looks exactly like this. We need some values for these blank spaces in front of grams and moles of copper. Where do we get those values? Well, notice that this is another molar mass, right? It's the ratio of grams to moles, or moles to grams. That's just a molar mass. So how do we find the molar mass of copper? That's right, we need to look at the periodic table. If you look up copper on the periodic table, you'll find that its molar mass is 63.55 grams of copper for each mole. And now we've completed the last step in our 3-step conversion. Let's take a look at the 3 steps all together. So first, over here, we're starting with our grams of copper sulfate pentahydrate, which we're converting into moles of copper sulfate pentahydrate. That's this conversion factor. Then we go from moles of copper sulfate pentahydrate into moles of copper. In this step, we're crossing the mole bridge. We then convert from moles of copper into grams of copper, using the molar mass of that element. So go ahead and pause the video and run this through your calculator. We'll compare answers after you unpause the video. So the final value that I have is 3.18 grams of pure copper can be isolated from 15 grams of copper sulfate pentahydrate. Now this is of course assuming a perfect extraction, a perfect refining process where we can get all of the copper out of this 15 grams. Notice that we have 3 significant figures in our final value, and that has to do with the fact that our first measurement here was also with 3 significant figures. You'll notice the other terms are either exact or have more sig figs. So for example, we have 5 significant figures here. These are exact because of the formula. This has 4 significant figures, and therefore 3 is the worst one, so our answer is also with 3 significant figures. So now that you've had a chance to see this process for the first time, let's go to the next page and try another example where you can test yourself and see how you're learning. So in this example, we're going to go through the same type of process. Let's read through it, and then I'll get you started on steps 1 and step 2. Okay, so here we go. Rocks called hematite, which have the formula Fe2O3. By the way, these are also just typical iron ore. They're called hematite. Anyway, hematite can be economically processed to extract pure iron metal, which can then be converted into steel for various applications and trade. So here's the main information we have. For every 100 grams of hematite, how much pure iron could be produced if we had a perfectly efficient process? So this is like, what if we dug out of the ground a bunch of this hematite ore and we wanted to refine it into iron? And actually, it turns out this is how we get iron metal for things like bridges and buildings and all that kind of stuff. So let's go through the process. First, in step 1, what I want you to do is figure out the formula mass, that is the molar mass for hematite. In step 2, you're going to start doing your conversions, and we're going to follow that same 3-step method. Because we don't have any direct conversion between grams of hematite and grams of iron, we have to use moles, and we have to cross the mole bridge. So we're going to need moles of hematite that we will convert into moles of iron by using this mole bridge that we will build. Now, because we're starting with grams of hematite, we're going to need to convert that grams of hematite into moles of hematite by using the molar mass. And then on the other side of this, we're going to need to convert our moles of iron into grams of iron because that's what we're interested in. In order to do that conversion, we're going to use the molar mass of iron. So those are the 2 steps. Go ahead and start with step 1, finding the molar mass of hematite. So if you add up 2 iron and 3 oxygen, you should get 159.70 grams per mole. Now let's go on to start with step 2. We need our starting point first, which is grams of hematite. And then we're going to do a conversion from grams of hematite into moles of hematite by using the molar mass. So we have our 100 grams, and we're multiplying that by the conversion factor with grams of hematite on the bottom and moles of hematite on the top. And then we just need our values here. Since we're talking about exactly 1 mole of hematite, we can find the mass by looking back at our molar mass, which is 159.70. And that brings us to the next step in the conversion, which is crossing the mole bridge. In this case, we're converting from moles of hematite into moles of iron. Therefore, we should have moles of hematite on the bottom and moles of iron in the top position. And we just need to have the right values here next to each of these units for this conversion factor. So where do we find those? Well, that's right. They're in the formula of hematite. Notice that if we had exactly 1 mole of hematite, so if there was a 1 here, that would mean we would have 2 moles of iron. So actually, hematite has quite a bit of iron in it. So now that we've crossed the mole bridge, what do we do next? Now we have to go from moles of iron into grams of iron, because that's what we're interested in the first place. So we're going to have a final conversion factor step over here where we're using the molar mass to go between moles of iron and grams of iron. So we should have 1 mole of iron at the bottom and the molar mass of iron at the top position, and it's 55.85 grams. Now, if you're wondering where I got the value 55.85 grams per mole of iron, take a look at the periodic table. You'll find that is the atomic mass for iron. So now let's just go through the calculation for this to figure out how much pure iron we could extract. So after we take our 100 and we divide it by 159.70, and then multiply that by 2, and then multiply that by 55.85, we get the final value of 69.94 grams of iron, which, if you think about it, tells us that there's about 70% iron by mass in hematite. And that brings us actually to the next section in the lesson, where we're going to learn about how to calculate the percent composition of an element in a given substance. To find the percentage that a particular element has by mass within a compound, we have a fairly straightforward formula to follow. We start with the molar mass of the element that we're interested in determining its percent composition. We multiply that molar mass by the number of atoms of that element in the formula. Finally, we divide by the molar mass of the entire compound and multiply this result by 100 to convert into a percentage. This percentage will tell us how much of a given element contributes to the total mass of a compound. Let's try this out with a few examples on the next page. Here in this first example, we're being asked, what is the percent composition of the element hydrogen in the compound water? Note, of course, the formula for water is H2O, so there are 2 hydrogen atoms for each water molecule. To find the percent composition of hydrogen, therefore, we need to multiply the molar mass of hydrogen by 2, because there are 2 hydrogen atoms, and then we need to divide by the molar mass of water. The molar mass of hydrogen can be found on the periodic table to be 1.008 grams per mole, and we need to multiply this by 2. Now we need to show the division by the molar mass of water. The molar mass of water is 18.02 grams per mole. So now we can do the calculation where we multiply 1.008 by 2 and then divide by 18.02. We multiply that result by 100 to give us our percentage. In this case, we find that hydrogen comprises 11.19% of the total mass of water. So now let's try this same thing but with oxygen. Go ahead and pause the video for a few moments and try to find the percent composition of oxygen in water. So if you calculated 88.79%, great job. You might have also done an alternative, which is subtract 11.19 from 100. They both give you similar results. If we actually did the calculation, though, it would look something like this. We would take the molar mass of oxygen, which is 16 grams per mole, and we're just multiplying it by 1 because there's only 1 oxygen atom. So we have 16 up here, and then we're dividing it again by 18.02 grams per mole because that's the molar mass of water. We multiply this result by 100 to give our 88.79. You'll notice if you add these two values up, you don't get to exactly 100. That has to do with the errors inherent on the molar masses from the periodic table, as well as rounding errors. So that's percent composition. Now let's go back to that previous page before we end this lesson and look at that example. I think now you have the tools necessary to solve that slightly difficult problem. Let's go take a look. So let's first read through this problem, and then I'll go through and try to describe one way that you could approach a solution. Suppose, for example, we had 10 grams of the hydrated salt of barium chloride. So it's called barium chloride dihydrate. We had 10 grams of it. Let's say we heated it until all of the water was driven off. How many grams of pure barium chloride would remain after we did this? Feel free to pause the video here, and you might come up with a creative solution of your own, or even the same one that I'm about to show you. When you unpause the video, we'll discuss. To help explain a solution for this problem, I want to use a visual diagram. These visual diagrams can be really helpful when you're first learning these types of problems and how to solve them. So let's talk about this. We have our starting material here, which is barium chloride dihydrate. So I've drawn the barium chloride as one thing here, and then the hydrates as two different things because we have two of them. So let's try to summarize this in terms of moles, for example. Suppose we had 1 mole of this stuff, which we don't because we only have 10 grams. But suppose we did for a minute. Suppose we had 1 mole. If we had 1 mole of this stuff before we heated it, let's think about how many moles we would have of all the different stuff after we heated it. Heating it, of course, we can show with a forward arrow and a little triangle under it. And what's going on when we heat it is we separate the water molecules from the barium chloride. So after heating, we have barium chloride over here, and then we have our water molecules over here. Now those water molecules, as they're being heated, actually go off into the vapor phase. So actually you can do this on a hot plate with some of this hydrated salt or others, and you can actually hear it sizzling and see kind of like steam coming off the crystals most of the time. So what do we have after we've heated it in terms of moles? Well, that's right, we have the number of moles of barium chloride. Has it changed? No, if we started with 1 mole of this stuff over here, after we heat it, we still have the same number of moles of it. We have 1 mole of this, and we have 2 moles of water. Because those 2 moles of water were on here, they were attached to it, now they're gone. So in the end, we still have 1 mole of barium chloride. You can think about this in terms of the molar conversion factors. We know that if we had 1 mole of barium chloride dihydrate, that is the same as saying we have 1 mole of barium chloride. We can also make another conversion factor relating water to the hydrated salt. For every mole of barium chloride dihydrate, there are 2 moles of water. Now what I want to do is show you how we can use these conversion factors to help us solve this problem. So let's go take a look at that below. As I mentioned earlier in the lesson, there's no direct path from the grams, say over here, of barium chloride dihydrate into the grams of barium chloride. But that's what we're trying to do, right? We're trying to get from grams of this into grams of this. Now, there's no direct pathway for grams to grams, but there is a direct pathway from moles to moles. Again, that's called the mole bridge. We can go from moles of A into moles of B using this conversion factor. We know that 1 mole of barium chloride dihydrate is equal to 1 mole of barium chloride. So we can do this. The question is how do we bring grams into this situation? So for example, how do we convert grams of barium chloride dihydrate into moles of barium chloride dihydrate? That's right, we need to use the molar mass of barium chloride dihydrate, which in this case I'm representing with the letter A. So once we've converted grams of A into moles of A, and then we cross the mole bridge from moles of A to moles of B, we then use the molar mass of B to give us grams of B. So it might seem a little bit tricky with this particular problem, but I want you to pause the video and see if you can start setting up some of these conversion factors. As you get stuck or as you complete the problem, just go ahead and unpause the video and I'll go through the solution step by step. The first thing we need to do is get our starting point and our first conversion factor ready to go. So we're starting here with 10 grams of this barium chloride hydrated salt. And then we need a conversion factor. Now let's take a look at what this conversion factor needs to do. We need to convert grams of barium chloride into moles of barium chloride. So we're going to need moles up here and grams down here. So this is what the first conversion factor will look like. This is our molar mass of A, or molar mass of barium chloride dihydrate. The value for this conversion factor, where we have exactly 1 mole of the hydrated salt, comes from just adding up barium, chlorine, and the water molecules like we did on the previous page in the lesson. So we have 244.25 grams for every mole. So that's our first step. We've converted grams of barium chloride into moles of barium chloride. What are we going to do next? Well, if we look at this diagram, we go from grams of A to moles of A, and then we have to cross the mole bridge. So we have to go from moles of this starting material into moles of this product, so moles of B. So let's set up our next conversion factor, taking that into account. So our mole bridge should look like this. We have moles of B up top, that's our barium chloride, and moles of A at the bottom, that's our hydrated salt. We just need to find the right values to put into these boxes. Where do we get those values? Well, that's right. We have to get those values from the actual conversion factors between those two different things. Notice here when I showed you this example up above as a diagram, we noted that 1 mole of the hydrated salt is going to produce 1 mole of this anhydrous salt because there's just one of those. We're getting rid of the waters, but we're not getting rid of that salt in the middle. So that means it's a 1-to-1 ratio. There's 1 mole of barium chloride dihydrate is equal to 1 mole of barium chloride. So let's go put those values into our conversion factor down here. So that's our second step that we've completed. We've converted moles of A into moles of B. We've crossed the mole bridge. Now what's our last step? We have to convert moles of B into grams of B. So we're going to need another conversion factor. And that conversion factor specifically needs to be the molar mass of B. So let's see how that's set up. Because we're converting from moles of barium chloride into grams of barium chloride, we need to have moles of barium chloride in the bottom position of the conversion factor and grams of barium chloride in the top position. Now we just need to find the right values that belong in these places for our conversion factor. Where do we find those values? Well, that's right, it's the molar mass of barium chloride, so we just have to add up all of the individual atomic masses. So if we add up barium and 2 chlorine atoms, we get 208.2 grams for each mole. And that completes our third step. So let's go ahead and do the complete calculation. We're going to take our 10 grams divided by 244.25. Then we're going to multiply by 1. And then we're going to multiply that by 208.2. That will give us our grams of barium chloride. My calculation gives 8.53 grams. If you got that right, great job. So it's kind of a tricky problem until you realize all you're doing is changing the molar mass of the thing that you're starting with to remove the water molecules. And with that, I'm going to end this lesson. Please make sure to practice some of these quantitative type problems with moles, molar mass, hydrated salts, etc. Please let me know if you have any questions, and I hope to see you soon. Take care.